Hello and welcome to Space Historians. I'm glad you found your way here tonight, ready to let the weight of the day fall away and drift gently into one of humanity's deepest questions. How will the universe end? It's a question that feels impossibly vast, yet also strangely comforting in its scope. A reminder that everything, even the cosmos itself, is part of a story with chapters yet unwritten. If you enjoy these quiet explorations through space and time, a like and subscribe help others discover this calm refuge. But for now, you don't need to do anything at all. Just settle in, breathe deeply, and let wonder carry you softward. There is something happening right now, this very moment, that sounds impossible until you understand it. The universe is expanding, not just growing slowly, but accelerating, racing outward faster with each passing second. Galaxies that were once neighbours are now rushing apart at speeds that defy intuition. The space between everything is stretching, and that stretching is speeding up. This acceleration is not some distant future concern or ancient history. It is occurring now, invisibly, silently, carrying the entire cosmos toward a fate that has fascinated and troubled scientists since its discovery. To picture this expansion, imagine the universe as a vast fabric being pulled in all directions at once. Every galaxy sits like a dot on that fabric, and as the fabric stretches, the dots move apart. The farther away two dots are, the faster they separate. Not because they're moving through space, but because space itself is growing between them. This is not an explosion from a single point, but an expansion of everything simultaneously. There is no centre, no edge, just endless stretching in all directions. The discovery of this expansion changed everything we thought we knew about the cosmos. For most of human history, people imagined the heavens as eternal and unchanging. Stars seemed fixed, constellations permanent. The night sky a stable backdrop against which earthly dramas unfolded. Even when telescopes revealed countless galaxies beyond our own, the assumption remained that the universe was essentially static, neither growing nor shrinking, simply existing in steady state through infinite time. But observations in the early 20th century shattered that comfortable picture. When astronomers measured the light from distant galaxies, they found something unexpected. The light was shifted toward the red end of the spectrum, stretched to longer wavelengths. This red shift indicated motion, specifically motion away from us. Every galaxy beyond our immediate neighbourhood was receding, and the pattern was clear. The farther away a galaxy was, the faster it appeared to be moving. The universe was not static, it was expanding. That realization alone was revolutionary, but it was only the beginning. If the universe is expanding now, then logically it must have been smaller in the past. Wind the clock backward, far enough, and you arrive at a moment when everything we see today was compressed into an unimaginably hot, dense state. That moment became known as the Big Bang. Though the name is misleading, it was not an explosion into empty space, but the beginning of space itself. The moment when expansion started. From that initial state, roughly 13.8 billion years ago, the universe has been growing and cooling ever since. For decades after discovering expansion, scientists assumed it would eventually slow down. After all, gravity pulls everything together. The mutual attraction of all the matter in the universe should act as a brake, gradually decelerating the expansion. Perhaps it would slow enough to stop entirely and then reverse, causing everything to collapse back into a dense state, a big crunch mirroring the Big Bang. Or perhaps the expansion would continue forever, but at an ever-decreasing rate, asymptotically approaching zero. Either way, the expansion was expected to decelerate over time. Then came another impossible discovery. In the late 1990s, two independent teams of astronomers studied distant supernovae, stellar explosions so bright they could be seen across billions of light years. These supernovae served as cosmic distance markers, allowing astronomers to measure how fast the universe was expanding at different times in its history. What they found contradicted all expectations. The expansion was not slowing down, it was speeding up. The universe's expansion was accelerating, driven by some mysterious force that seemed to push space apart. This acceleration is the impossible beginning of our story about the universe's fate. It suggests that something invisible, something that interacts with nothing, except through its effect on the expansion of space, dominates the cosmos. Scientists named it dark energy, though the name reveals how little we understand it. Dark because it does not emit, absorb, or reflect light. Energy because it seems to be a property of space itself, a kind of intrinsic pressure that grows stronger as space expands. The implications are staggering. If dark energy continues to drive acceleration, then the universe will not slow down, will not stop, will not collapse. Instead, it will expand forever, faster and faster, carrying galaxies beyond the reach of light, eventually stretching space itself to unimaginable distances. The stars that light our night sky will fade one by one as they drift beyond the cosmic horizon. Galaxies will become isolated islands in an increasingly empty void. The universe will grow colder, darker, emptier, until nothing remains but silence stretched across infinite space. This accelerating expansion sets the stage for everything that follows. It determines the universe's fate more surely than any other factor. Understanding how it was discovered, what drives it, and where it leads requires patience and careful thought. But even now, at the beginning of this journey, one thing is clear. The universe is not static. It is not eternal in the way people once imagined. It is a dynamic, evolving system moving inexorably toward a distant future that will look nothing like the present. And that future begins with expansion, with acceleration, with the impossible fact that the cosmos is racing outward faster every moment. Tonight, as you rest, imagine that expansion continuing. Imagine space stretching, galaxies drifting, the fabric of reality pulling itself apart so slowly that no human lifetime could ever detect it, yet so surely that over eons it will reshape everything. That is the impossible beginning, the fact from which all cosmic futures flow. Long before anyone understood expansion or acceleration, long before telescopes revealed galaxies or equations described space-time, people wondered about endings. They looked at the cycles around them, day giving way to night, seasons turning, lives beginning and ending, and they asked whether the universe itself might follow a similar pattern. Did time stretch infinitely in both directions, or did it have boundaries, moments of creation and conclusion? These questions were not scientific in the modern sense, but they were the seeds from which cosmology would eventually grow. Ancient Greek philosophers debated whether the cosmos was eternal or created. Some, like Aristotle, argued for an eternal universe with no beginning and no end, a perfect, unchanging realm beyond the imperfect, changing world of human experience. Others imagined cycles, worlds born from chaos, evolving through ages of harmony, then dissolving back into formlessness before being reborn. These cycles echoed the patterns they saw in nature: death followed by rebirth, winter giving way to spring, the eternal return of familiar forms. In Hindu cosmology, time itself was cyclic, measured in vast epochs called kalpas. Each kalpa represented billions of years during which the universe would unfold, exist, and then dissolve, only to be reborn in the next cycle. These were not mere myths, but profound attempts to make sense of existence on the largest possible scale. The idea that the universe might have a rhythm, a heartbeat of creation and destruction, resonated across cultures and centuries. Other traditions imagined linear time with a definite beginning and a prophesied end. Creation narratives described how order emerged from void, how light separated from darkness, how structure arose from chaos. End times were foretold, apocalyptic visions where the heavens would be rolled up like a scroll, where fire would consume the earth, where a new creation would emerge from the ashes of the old. These stories were not cosmology as we understand it today, but they grappled with the same fundamental question. What is the ultimate fate of everything? Medieval scholars, working within religious frameworks, tried to reconcile observation with scripture. They debated whether the heavens were eternal or created, whether the stars were fixed or moving, whether time had a beginning and would have an end. Some proposed that while earthly things were temporary, the celestial realm was eternal, unchanging. perfect. Others saw change everywhere and wondered whether even the heavens were subject to decay. The scientific revolution began to shift these questions from philosophy and theology toward observation and mathematics. When Copernicus proposed that Earth orbited the Sun rather than sitting at the centre of everything, he set in motion a transformation of thought. If Earth was not central, perhaps the universe did not revolve around human concerns. Perhaps it operated according to laws that could be discovered, tested, and described with precision. Galileo's telescopes revealed that the heavens were not perfect and unchanging. The moon had mountains and valleys. The sun had spots. Jupiter had moons that orbited it, proving that not everything circled Earth. These observations chipped away at the old certainties, revealing a universe more complex and dynamic than tradition suggested. If the heavens could change, if celestial bodies could move and evolve, then perhaps the cosmos itself had a history, a trajectory, possibly even an eventual fate. Newton's laws of motion and gravity provided a framework for understanding how objects moved, how forces acted across empty space, how the planets traced their paths around the sun. But Newton himself struggled with the implications for the universe as a whole. If gravity pulled everything together, why did the stars not collapse into a single massive clump? He suggested that perhaps the universe was infinite, with stars spread so evenly that their mutual attraction balanced out. It was an elegant idea, but it left unresolved questions about stability and time. By the 19th century, thermodynamics introduced a new concept that would prove crucial for understanding cosmic fate. The second law stated that entropy, a measure of disorder, always increases in a closed system. Energy spreads out, differences diminish, heat flows from hot to cold until everything reaches equilibrium. Applied to the universe as a whole, this suggested a troubling possibility. If the cosmos was a closed system, then over vast spans of time, all the energy differences that drive stars, motion, and life would gradually fade. The universe would reach a state of maximum entropy, a heat death where nothing more could happen. This idea of heat death troubled thinkers in the late 1800s. It suggested that the universe, however magnificent, was winding down like a clock, destined eventually for stillness and silence. Some found this prospect bleak, a cosmic pessimism that seemed to rob existence of ultimate meaning. Others saw it as simply another stage in understanding, a logical consequence of physical laws applied consistently across time. But heat death was only one possibility, one scenario derived from thermodynamics applied to an assumed static universe. What if the universe was not static? What if it expanded or contracted? What if new physical principles, not yet discovered, altered the picture? These questions remained unanswered as the 19th century gave way to the 20th, setting the stage for discoveries that would revolutionize our understanding of cosmic fate. Where it all began then was not in a laboratory or with a telescope, but in the human impulse to ask about endings, to wonder whether the story of existence had a conclusion, and if so, what form it might take. From ancient myths of cycles and apocalypses, through medieval debates about eternity and creation, to scientific explorations of entropy and heat death, humanity has always looked toward the distant future and asked, how will it all end? That question, refined and sharpened by centuries of thought, became the foundation for modern cosmology's attempts to map the universe's ultimate fate. In the 1920s, Edwin Hubble stood at the eyepiece of the most powerful telescope in the world, the 100-inch reflector on Mount Wilson in California. Night after night, he photographed distant galaxies, those faint smudges of light that earlier astronomers had called nebulae. Some thought these nebulae were clouds of gas within our own Milky Way. Others suspected they might be separate galaxies, island universes scattered across vast stretches of space. Hubble set out to measure their distances and settle the question once and for all. Using a technique involving Cepheid variable stars, whose brightness fluctuates in predictable patterns, Hubble calculated that some of these nebulae were indeed far beyond the Milky Way. They were galaxies in their own right, each containing billions of stars, separated from us by millions of light years. This discovery alone was revolutionary, expanding the known universe enormously. But Hubble noticed something else. Something even more profound. The light from these distant galaxies was shifted toward the red end of the spectrum. This red shift was not random. It followed a pattern. The farther away a galaxy was, the more its light was shifted toward longer wavelengths. Red shift indicated motion, specifically motion away from the observer. Just as the pitch of a siren drops as an ambulance speeds away, the wavelength of light stretches when its source is receding. Hubble's observations showed that nearly every galaxy beyond our immediate neighbourhood was moving away from us. And the more distant the galaxy, the faster it appeared to recede. In 1929, Hubble published his findings. The relationship between distance and velocity was clear, proportional, and consistent. Galaxies twice as far away were receding twice as fast. This relationship, now called Hubble's law, had staggering implications. If all galaxies were moving apart, then the universe itself must be expanding. Space was not a static stage on which cosmic events unfolded, but a dynamic medium, stretching and carrying galaxies along with it. The discovery was met with both excitement and skepticism. Some scientists immediately recognized its importance. If the universe was expanding now, then it must have been smaller in the past. Extrapolate backward, and you reach a moment when everything was compressed together, a cosmic beginning. Others found the idea unsettling. An expanding universe challenged the notion of an eternal, unchanging cosmos. It suggested that the universe had a history, an age, possibly even an origin. Albert Einstein, who had developed the general theory of relativity years earlier, initially resisted the idea of expansion. His equations actually predicted that the universe should either expand or contract. But he found that results so counterintuitive that he added a term called the cosmological constant to keep the universe static. When Hubble's observations confirmed expansion, Einstein reportedly called the cosmological constant his greatest blunder. The universe was not static after all. It was growing. The expansion Hubble discovered raised immediate questions about the universe's fate. If gravity was pulling everything together, would expansion eventually slow down? Would it stop and reverse, leading to a collapse? Or would it continue forever, gradually decelerating but never quite halting? The answer depended on the total amount of matter in the universe and the strength of gravity's pull. Too much matter and gravity would win, pulling everything back together. Too little, and expansion would continue unimpeded. For decades, astronomers worked to measure the density of matter in the universe, trying to determine which fate awaited. They counted galaxies, estimated their masses, and calculated whether there was enough gravitational attraction to eventually halt expansion. The measurements were difficult and uncertain, but a picture began to emerge. The universe seemed to be hovering near a critical threshold, neither dense enough to collapse nor sparse enough to expand forever at a steady rate. The fate of the cosmos appeared balanced on a knife's edge. Hubble's discovery also implied something profound about the nature of space. Expansion was not galaxies flying through pre-existing empty space, like shrapnel from an explosion. It was space itself stretching, carrying galaxies along. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move apart, not because they're travelling across the rubber, but because the rubber itself is expanding. In the same way, galaxies recede because the space between them is growing. This understanding transformed cosmology from a philosophical pursuit into an observational science. The universe had a measurable history and a predictable future, at least in principle. By measuring expansion rates, matter densities, and gravitational effects, scientists could forecast cosmic destiny. Hubble's discovery provided the first solid evidence that the universe was not eternal and unchanging, but dynamic and evolving. It opened the door to asking meaningful questions about ultimate fate. Think about what it must have felt like for Hubble and his contemporaries to realize what they were seeing. The night sky, which had seemed so fixed and permanent, was actually filled with galaxies rushing apart. The universe was not a completed creation, but an ongoing process, unfolding in time. Every observation of distant light was a glimpse into the past, a snapshot of how things were when that light began its journey. The farther astronomers looked, the younger the universe appeared, stretched out across billions of years like a cosmic timeline. Hubble's discovery was the beginning of modern cosmology, the moment when questions about the universe's fate moved from speculation to science. Before him, people wondered whether the cosmos was eternal or created, cyclic or linear, finite or infinite. After him, those questions could be approached with telescopes and mathematics. The universe's expansion rate could be measured, its history could be reconstructed, its future could be modelled. The discovery did not answer every question, but it provided the foundation for everything that followed. And so, standing on Mount Wilson in the cool night air, peering through the eyepiece of a massive telescope, Edwin Hubble changed humanity's understanding of existence. He showed that the universe was not static but moving, not eternal but evolving, not a finished product but an unfolding story. That story continues today, written in the light of distant galaxies, in the equations of general relativity, in the observations of countless astronomers building on what Hubble began. The discovery of expansion was the key that unlocked the door to understanding cosmic fate, and through that door, we glimpse possibilities both wondrous and sobering. When Edwin Hubble announced that distant galaxies were receding and that the universe was expanding, the scientific community responded with a mixture of wonder and doubt. The idea was so radical, so contrary to centuries of assumption, that many struggled to accept it. For generations, astronomers had assumed the cosmos was essentially unchanging on the largest scales. Stars might be born and die, planets might form and erode, but the universe as a whole was thought to be eternal and static. Now Hubble was suggesting that everything was in motion, that space itself was growing, carrying galaxies apart like leaves on an expanding pond. The awe came from the elegance of the discovery. Hubble's observations fit together beautifully. The red shifts increased with distance in a simple, proportional relationship. The pattern was clear and consistent across the entire visible universe. It suggested that the cosmos operated according to understandable laws, that its behavior could be predicted and measured. For those willing to embrace the implications, it was a thrilling moment, a leap forward in humanity's understanding of reality. But disbelief was equally strong. Some scientists questioned the measurements. Red shift could have other causes, they argued. Perhaps light lost energy as it travelled across vast distances, stretching its wavelength without requiring expansion. Perhaps there was some unknown physical process affecting distant light. Perhaps the observations were being misinterpreted. These objections were not unreasonable. Science demands skepticism, especially when confronted with extraordinary claims, and the claim that the entire universe was expanding certainly qualified as extraordinary. Albert Einstein himself resisted initially. He had developed the general theory of relativity, which predicted that the universe should either expand or contract based on its matter and energy content. But Einstein found this result so counterintuitive that he modified his equations with the cosmological constant, a term designed to keep the universe static. When Hubble's observations confirmed expansion, Einstein reluctantly accepted that his original equations had been correct all along. The universe was not static, and his attempt to force it into stasis had been unnecessary. Other prominent astronomers struggled with the implications. If the universe was expanding, then running time backward suggested a beginning, a moment when everything was compressed together. This idea became known as the Big Bang, though the name was coined mockingly by Fred Hoyle, a proponent of an alternative steady-state theory. Hoyle and others found the notion of a cosmic beginning philosophically troubling. It seemed to introduce a moment of creation, raising uncomfortable questions about what came before and what caused it. The debate between expanding universe models and steady-state models persisted for decades. Proponents of steady-state argued that while the universe expanded, new matter was continuously created to fill the growing space, maintaining a constant average density. In this view, the universe had no beginning and would have no end. It simply was, eternally expanding yet always looking roughly the same. This model appealed to those who preferred an eternal cosmos without singular moments of creation or destruction. Evidence gradually accumulated in favour of expansion. Observations grew more precise. Theoretical work showed how expansion could explain the cosmic microwave background, a faint glow of radiation filling the entire sky. This background radiation was predicted by Big Bang models as the cooled remnant of the universe's hot, dense, early state. When it was discovered in 1965 by Arno Penzias and Robert Wilson, it provided strong support for expansion and effectively ended the steady-state debate. The universe did have a history, a beginning, an evolution. Yet even with growing acceptance of expansion, questions remained about the universe's ultimate fate. If it was expanding now, would it expand forever? The answer depended on factors that were difficult to measure: the total amount of matter and energy in the universe, the strength of gravity's pull, the geometry of space itself. Different assumptions led to different conclusions. A dense universe would eventually stop expanding and collapse. A sparse universe would expand forever, but at a decelerating rate. A finely balanced universe might expand forever at an ever-slowing pace, asymptotically approaching zero growth. The emotional response to these possibilities varied. Some found the idea of eternal expansion comforting, a cosmos without a final catastrophic collapse. Others found it bleak, imagining a universe growing colder, darker, emptier, until nothing meaningful remained. The prospect of a big crunch, a reversal of expansion leading to collapse, held a kind of symmetry, an ending that mirrored the beginning. But it also meant an eventual destruction of everything, all structures crushed out of existence. What made this period so fascinating was not just the scientific debate but the philosophical one. People were grappling with what it meant to live in a universe that had a history and would have a future. If the cosmos was not eternal, if it began in a big bang and would end in either endless expansion or eventual collapse, then humanity's place in the story became clearer and more poignant. We existed during the middle chapters, in the era when stars shone and galaxies glittered. Before the long twilight or sudden end, the awe and disbelief surrounding Hubble's discovery reflected deeper tensions about certainty and change. Human beings crave stability, permanence, the sense that some things are fixed and reliable, the realization that even the universe itself was subject to change, that it evolved and would continue evolving towards some distant fate, challenged that desire. It required accepting that nothing was eternal, not even the grand stage on which existence played out. Yet there was also beauty in the discovery. To know that the universe was expanding meant that every measurement, every observation, every photon of light carried information about cosmic history and destiny. The night sky became a living record, a map not just of space but of time. Each galaxy's red shift told a story of motion and distance. Each measurement refined our understanding of where the cosmos came from and where it was going. Awe and disbelief gave way, gradually, to acceptance and wonder as humanity adjusted to its place in a dynamic, evolving universe. Once scientists accepted that the universe was expanding, a logical question arose. Would expansion continue forever, or would it eventually halt and reverse? The answer seemed straightforward. Gravity, the force that held galaxies together and pulled stars into orbits, should act as a brake on expansion. Every bit of matter in the universe attracted every other bit, and while individual galaxies might be too far apart to significantly influence each other, the cumulative effect of all matter should slow the expansion over time. The more matter, the stronger the braking effect. Eventually, if there was enough matter, gravity would win, halting expansion and pulling everything back together in a big crunch. But observations revealed a contradiction. When astronomers measured the mass of galaxies, counting stars and estimating their combined gravitational pull, the numbers did not add up. There was not enough visible matter to account for the gravitational effects they observed. Galaxies rotated too fast for their visible mass. Clusters of galaxies held together more strongly than the luminous stars and gas could explain. Something invisible was providing extra gravity, holding structures together that should have flown apart. This invisible mass became known as dark matter. It does not emit, absorb, or reflect light, making it undetectable by telescopes. Its presence is inferred only through gravitational effects. When dark matter was included in calculations, the total mass of the universe increased significantly, enough that some models predicted expansion would eventually slow to a halt. But even with dark matter, the question remained open. Was there enough total mass, visible and dark combined, to stop expansion? Or would the universe continue growing forever? Throughout the 1980s and 90s, astronomers refined their measurements, trying to determine the universe's density and geometry. They mapped galaxy distributions, measured cosmic expansion rates at different distances, and studied the cosmic microwave background for clues about the universe's composition. The results hinted that the universe was close to a critical density, the precise amount of matter needed to make space flat, neither curved inward like a sphere nor outward like a saddle. A flat universe would expand forever, but at an ever-decreasing rate, asymptotically approaching zero growth. Yet a contradiction lurked in these measurements. Different techniques gave slightly different answers. Some suggested the universe was slightly below critical density, destined to expand forever. Others hinted it was slightly above, possibly leading to eventual collapse. The uncertainty was frustrating, but it reflected the difficulty of measuring cosmic properties. The universe is vast, and our observations are limited to a small region. Extrapolating from what we can see to the cosmos as a whole requires assumptions and careful analysis. Then came a discovery that deepened the contradiction. In the late 1990s, two independent teams of astronomers studied distant supernovae, explosions of white dwarf stars that could be seen across billions of light years. These supernovae served as standard candles, objects whose intrinsic brightness was known. By measuring how bright they appeared from Earth, astronomers could calculate their distances. Comparing those distances to the red shifts of their host galaxies allowed precise measurements of how fast the universe was expanding at different times in its history. The expectation was clear. Expansion should be slowing down due to gravity. Distant galaxies, whose light showed the universe billions of years ago, should be receding slower than nearby galaxies. The expansion rate should decrease over time as gravity exerted its braking effect. But the observations showed the opposite. Distant supernovae appeared fainter than expected, meaning they were farther away than a decelerating expansion would predict. The universe's expansion was not slowing down, it was speeding up. This result contradicted everything astronomers thought they knew about cosmic fate. If expansion was accelerating, then some force was pushing space apart, overwhelming gravity's pull. That force, whatever it was, did not fit into existing models. Gravity always attracts, pulling things together. What could be pushing them apart? The discovery was so unexpected that both research teams initially questioned their own data, checking and rechecking for errors. But the results held. Acceleration was real. The contradiction was profound. Decades of work had assumed that gravity was the dominant force shaping cosmic fate. The only question was whether there was enough matter to eventually halt expansion. Now it appeared that matter, whether visible or dark, was not the whole story. Something else filled the universe. Something that exerted negative pressure, pushing space apart. This mysterious component became known as dark energy, though the name revealed how little was understood about it. Dark energy did not fit easily into physics. It could not be ordinary matter or radiation. It did not clump into galaxies or interact with particles in any familiar way. It seemed to be a property of space itself, a kind of vacuum energy that became stronger as space expanded. The more the universe grew, the more dark energy it contained, and the faster expansion accelerated. If this interpretation was correct, then the universe's fate was no longer balanced between expansion and collapse. It was tipping decisively toward eternal, accelerating expansion. The contradiction between expectation and observation forced a rethinking of cosmic destiny. Instead of a universe gradually winding down, slowing its expansion as gravity acted over eons, astronomers confronted a cosmos racing toward increasing isolation. Galaxies would be carried apart faster and faster until they slipped beyond the cosmic horizon, their light unable to reach us across the ever-widening gulf of space. The universe would not end in fire or ice in the traditional sense, but in loneliness, with each galaxy eventually isolated in its own bubble of observable space, unable to see or interact with the rest of the cosmos. This contradiction was not a failure of science, but a triumph of observation over expectation. It showed that the universe was stranger than anyone had guessed, that assumptions based on incomplete knowledge could be overturned by careful measurement. The discovery of accelerating expansion opened a new chapter in cosmology, one focused on understanding dark energy and its implications for the universe's ultimate fate. The contradiction revealed that the cosmos was not winding down passively, but actively evolving toward a future radically different from its past. Once the contradiction was clear, once astronomers accepted that expansion was accelerating rather than slowing, the question shifted from observation to explanation. What possible futures awaited a universe dominated by dark energy? Three main scenarios emerged from the mathematics of general relativity and thermodynamics, each painting a different picture of cosmic fate. These were not wild speculations, but careful extrapolations based on known physics, reasonable assumptions, and measurable properties of the universe. They became known as the heat death, the big crunch, and the big rip. The heat death scenario emerged from thermodynamics, specifically the second law, which states that entropy always increases in a closed system. Applied to the cosmos, this meant that over vast timescales, energy would spread out, differences would diminish, and the universe would drift toward equilibrium. In this future, expansion continues forever, driven by dark energy. Galaxies drift apart, star formation gradually ceases as gas is used up, and existing stars burn through their fuel. Over trillions of years, even the longest-lived red dwarfs exhaust their hydrogen and fade. What remains after the stars die are their remnants, white dwarfs, neutron stars, and black holes. These objects persist for unimaginable spans of time, cooling and fading into darkness. Eventually, even black holes evaporate through Hawking radiation, a quantum effect that causes them to slowly lose mass. When the last black hole disappears, the universe is left with only a thin soup of particles and photons, spread so thinly across expanding space that interactions become impossibly rare. This is heat death, not a sudden catastrophe but a gradual fading into uniform, cold silence. The Big Crunch represents a different possibility, one where expansion eventually reverses. If dark energy were not constant, if it weakened over time or changed its nature, gravity might eventually regain control. Expansion would slow, halt, and then reverse. Galaxies would begin falling toward one another, slowly at first, then faster as distances decreased and gravitational attraction strengthened. Over billions of years, the universe would contract, temperatures would rise, and structures would merge. In this scenario, the end mirrors the beginning. As contraction continues, galaxies collide and merge, stars are torn apart by tidal forces, and space itself curves inward. Eventually, everything is compressed into a dense, hot state similar to the early universe just after the Big Bang. Whether this leads to total annihilation or to a bounce, a new Big Bang beginning another cycle, remains uncertain. The Big Crunch offers a kind of symmetry, an ending that echoes the beginning, though it requires dark energy to behave differently than current observations suggest. The Big Rip is the most dramatic and violent scenario. It assumes that dark energy not only drives acceleration, but grows stronger over time. If the repulsive effect of dark energy increases, then expansion does not just continue, it runs away. At first, the effect is subtle, galaxies recede faster than expected, but as dark energy strengthens, its influence spreads inward, affecting smaller and smaller scales. Galaxy clusters are pulled apart, individual galaxies dissolve, solar systems disintegrate. Eventually, dark energy becomes strong enough to overcome even the forces holding atoms together. Planets are torn from their orbits. Stars are ripped apart. Molecules are shattered. Atoms themselves are pulled into constituent particles. In the final moments, even space-time is torn, ripped into a state where the concept of distance loses meaning. The Big Rip happens quickly compared to heat death, possibly within tens of billions of years rather than trillions. It is an apocalyptic ending, a universe literally torn to shreds by its own expansion. Each theory rests on different assumptions about dark energy. Heat death assumes dark energy is constant, a cosmological constant as Einstein once proposed. The Big Crunch requires dark energy to weaken or reverse, allowing gravity to dominate. The Big Rip demands that dark energy strengthens, growing more powerful as space expands. Current observations favour the first scenario, suggesting dark energy is roughly constant, leading toward heat death. But uncertainties remain. Dark energy is so poorly understood that other possibilities cannot be ruled out. Beyond these three main scenarios, variations and alternatives exist. Some theories propose cyclic models where the universe oscillates between expansion and contraction. Big bangs, followed by big crunches in an eternal rhythm. Others suggest that our universe is one bubble in a vast multiverse, with different regions experiencing different fates. Still others invoke quantum effects, proposing that vacuum fluctuations could trigger new universes to sprout from the dying embers of old ones. These ideas remain speculative, but they show that the question of ultimate fate is far from settled. What makes these theories compelling is not just their scientific basis, but their philosophical resonance. Heat death evokes a slow, quiet ending, entropy's final victory, a universe that exhausts itself and falls silent. The Big Crunch offers closure and symmetry, an ending that mirrors the beginning, suggesting cosmic cycles or final annihilation. The Big Rip presents violence and rupture, a tearing apart of the very fabric of existence. Each theory reflects different ways of thinking about endings, about whether the universe fades, returns, or shatters. For us, contemplating these theories is an exercise in perspective. None of these endings will occur within human timescales, or even within the lifetime of our sun and solar system. They unfold across billions, trillions, or quadrillions of years, spans of time so vast that they make all of human history feel like a single heartbeat. Yet knowing these possibilities changes how we see the present. We live in a universe that is not eternal, not static, but evolving toward one of these distant fates. The theories also reveal the limits of knowledge. We can extrapolate from what we observe, we can apply physical laws consistently, we can calculate probable futures, but certainty eludes us. Dark energy remains mysterious. The long-term behavior of the universe depends on properties we do not yet fully understand. The theories are our best guesses, refined by observation and tested against data, but they remain provisional. The universe may surprise us again, just as it did with accelerating expansion. New discoveries could reveal new possibilities, futures we have not yet imagined. And so the theories stand as markers, signposts pointing toward possible destinations. Heat death, Big Crunch, Big Rip. Each a different ending written in the language of physics, each a different answer to the question of how it all ends. They invite contemplation, not dread. They remind us that even the cosmos is temporary, that everything, no matter how vast, is part of a story with chapters yet unwritten. The theories do not diminish the universe's grandeur. They reveal it, showing that even endings can be profound, even silence can be meaningful, even the distant future can teach us about the present. Understanding the universe's fate required more than theory. It demanded observation, measurement, and the patient accumulation of data across decades. Once the possibility of accelerating expansion emerged, astronomers launched a pursuit to understand dark energy, the mysterious force driving cosmic destiny. This pursuit involved building new telescopes, developing sophisticated instruments, and dedicating countless nights to observing distant supernovae, mapping galaxy distributions, and measuring the cosmic microwave background with unprecedented precision. The challenge was immense. Dark energy does not emit light, does not clump into structures, does not interact with ordinary matter in any detectable way, except through its effect on the expansion of space. Measuring it required indirect methods, observations sensitive enough to detect subtle changes in expansion rate across billions of years of cosmic history. It meant looking at the universe not as it is now, but as it was at different times, using the fact that light takes time to travel as a kind of cosmic time machine. One approach focused on supernovae, specifically Type Ia supernovae, explosions of white dwarf stars. These events are remarkably consistent in brightness, making them excellent standard candles. By measuring how bright they appear from Earth and comparing that to their known intrinsic brightness, astronomers could calculate precise distances. Matching those distances to redshifts gave expansion rates at different epochs. If dark energy was constant, the expansion rate would show a specific pattern. If it varied, the pattern would differ. The pursuit was to measure enough supernovae across enough distances to map that pattern precisely. Teams of astronomers competed and collaborated, scanning the sky for supernovae, following up discoveries with detailed observations, building catalogues of hundreds and eventually thousands of events. Each supernova added a data point, refining the picture of cosmic expansion. The work was painstaking. Supernovae are rare, appearing randomly in distant galaxies. Detecting them required monitoring vast swathes of sky repeatedly, looking for faint points of light that had not been there before. Then came spectroscopy, measuring the light in detail to confirm the type and distance. Another pursuit involved mapping the large-scale structure of the universe. Galaxies are not distributed randomly, but form patterns, filaments and clusters separated by vast voids. These patterns were seeded by tiny fluctuations in density in the early universe, amplified over billions of years by gravity. By surveying millions of galaxies, measuring their positions and redshifts, astronomers could reconstruct the cosmic web and compare it to predictions from different models of dark energy. The distribution of galaxies carries information about how expansion has evolved. The cosmic microwave background provided another crucial piece. This faint radiation, the cooled remnant of the Big Bang, fills the entire sky with nearly uniform temperature. But tiny, variations exist, hot and cold spots differing by millionths of a degree. These variations reflect density differences in the early universe, the seeds from which galaxies would later grow. By measuring these fluctuations precisely, missions like COBE, WMAP, and Planck mapped the early universe in exquisite detail. The patterns revealed the universe's geometry, composition, and expansion history, including the influence of dark energy. Each method had strengths and weaknesses. Supernovae provided direct distance measurements, but were rare and required careful calibration. Galaxy surveys covered vast volumes, but depended on complex models of structure formation. The cosmic microwave background offered a pristine snapshot of the early universe, but required sophisticated analysis to extract information. By combining all three approaches, astronomers could cross-check results, testing whether different methods agreed and building confidence in the emerging picture. The pursuit was not just technical but collaborative. Astronomers from around the world shared data, compared notes, debated interpretations. International consortiums formed to build next-generation telescopes and instruments. Space agencies launched satellites dedicated to cosmology. The Dark Energy Survey, the Sloan Digital Sky Survey, the Baryon Oscillation Spectroscopic Survey. Each project added pieces to the puzzle. The pursuit became a collective effort, generations of scientists building on the work of those before them. What drove this pursuit was not just curiosity, but a sense of profound importance. Understanding dark energy meant understanding the universe's fate. It meant knowing whether the cosmos would expand forever or eventually reverse, whether galaxies would drift into isolation or collapse together, whether the future held silence or cataclysm. These were not abstract questions, but fundamental truths about existence, and they demanded answers built on solid observational ground. The pursuit also revealed humility. Despite decades of effort, dark energy remains mysterious. We know it exists because we observe its effects. We can measure how much of the universe's energy budget it comprises, about 68%. We can track how expansion has accelerated over time, but we do not know what it is. Is it truly a cosmological constant, an intrinsic property of space? Is it a dynamic field that changes over time? Is it a sign that general relativity breaks down on cosmic scales? These questions remain open. For those engaged in the pursuit, the not knowing was part of the appeal. Science thrives on mystery, on unanswered questions that demand investigation. Each new measurement refined the constraints on dark energy's properties, narrowing the range of possibilities. Each new telescope pushed observations deeper into space and further back in time. The pursuit continued not because the answer was obvious, but because it remained tantalizingly out of reach, promising that the next observation might reveal something transformative. And so the pursuit goes on. New missions are planned, new instruments designed, new surveys launched. The James Webb Space Telescope peers into the distant universe, capturing galaxies as they appeared billions of years ago. The Vera Rubin Observatory will map the entire visible sky repeatedly, tracking changes and discovering supernovae by the thousands. Gravitational wave detectors listen for ripples in space-time from colliding black holes, offering yet another window into cosmic expansion. Each advancement brings us closer to understanding dark energy, and with it, the universe's ultimate fate. The pursuit is patient, methodical, and unending. It mirrors the cosmos itself, unfolding slowly across time, revealing secrets incrementally. For those who dedicate their careers to this work, the reward is not immediate answers but gradual clarity. The satisfaction of contributing to humanity's understanding of existence. And for the rest of us, following from a distance or simply gazing at the night sky, the pursuit offers comfort. Someone is asking these questions, someone is measuring, someone is seeking to understand how it all ends. We may not live to see the final answer, but the pursuit ensures that the question remains alive. The data arrived slowly, methodically, like pieces of a vast puzzle scattered across time and space. Each observation added a pixel to the emerging picture of cosmic fate. Supernovae flickering in distant galaxies, galaxy surveys mapping millions of points of light, satellites measuring the faint glow of the early universe. All of it converged into a coherent story about dark energy and expansion. The data was not dramatic in the moment. It consisted of numbers, spectra, images, measurements that meant little individually but revealed profound truths when assembled and analysed. The supernova data came from multiple teams observing independently. They photographed the same regions of sky repeatedly, comparing images to detect new points of light. When a supernova appeared, telescopes swung into action, capturing detailed spectra to measure redshift and brightness. Each measurement was painstaking. Distant supernovae were faint, requiring long exposures and careful calibration. Atmospheric effects, instrumental errors, and cosmic dust could all distort the signal. The data had to be cleaned, corrected, and cross-checked before it could be trusted. What emerged from this effort was a pattern. Distant supernovae, those showing high redshifts indicating they were far away, appeared dimmer than expected. If expansion had been decelerating, as gravity would suggest, those distant events should have appeared brighter. The fact that they were dimmer meant they were farther away than a decelerating model predicted. The universe's expansion had accelerated over time. The data was consistent across both research teams, confirmed by independent observations and aligned with theoretical expectations for a universe dominated by dark energy. The precision of the data was remarkable. Astronomers could measure distances to an accuracy of a few percent, tracking expansion rates across billions of years. They could see how the universe behaved when it was half its current age, when dark energy was just beginning to dominate over matter. The data showed a transition point, an era when matter's gravity still held sway, followed by a period when dark energy took over and acceleration began. This transition, occurring roughly 5 billion years ago, marked a turning point in cosmic history. Galaxy surveys added another dimension. By mapping the positions of millions of galaxies, astronomers traced the cosmic web. The large-scale structure of filaments and voids. This structure grew from tiny density fluctuations in the early universe, amplified by gravity over billions of years. The size and distribution of these structures depended on how fast the universe expanded during their formation. By comparing observed structures to computer simulations, astronomers could constrain dark energy's properties. The data matched models where dark energy was roughly constant, supporting the cosmological constant interpretation. The cosmic microwave background provided yet more data. Satellites like Planck measured temperature variations across the entire sky with extraordinary precision, mapping fluctuations down to millionths of a degree. These variations contained information about the universe's geometry, composition, and expansion history. By analysing their patterns, cosmologists extracted values for key parameters. The universe's age, its matter density, its dark energy content. The data confirmed that dark energy constituted about 68% of the universe's total energy budget, with dark matter at 27% and ordinary matter only 5%. What made the data powerful was its consistency. Different methods, observing different aspects of the universe, converged on the same conclusions. Supernovae, galaxy surveys, and the cosmic microwave background all pointed toward a universe dominated by dark energy, expanding at an accelerating rate. This convergence built confidence. When independent lines of evidence agree, the result is more trustworthy than any single measurement. The universe was telling a coherent story through multiple channels, yet the data also revealed uncertainties. Measurements of the expansion rate, the Hubble constant, gave slightly different values depending on method. Observations of the local universe suggested one value, while extrapolations from the cosmic microwave background suggested another. This tension hinted at either systematic errors or new physics. Perhaps dark energy was not perfectly constant. Perhaps the universe's expansion history was more complex than simple models suggested. The discrepancies were small but persistent, driving ongoing research. Recording the data required global collaboration. Observatories in Chile, Hawaii, Australia, and space contributed observations. Data flowed into centralized archives, where researchers worldwide could access it. Analysis involved sophisticated algorithms, statistical techniques, and computational power. Teams spent years refining methods, testing for biases, and ensuring robustness. The data was not just raw numbers, but the product of human ingenuity, persistence, and cooperation across borders and disciplines. For those working with the data, each new measurement brought excitement. Every supernova added precision. Every galaxy survey expanded the sample. Every refinement of the cosmic microwave background map sharpened the picture. The data transformed abstract theories into quantified reality. Dark energy was no longer just a concept, but a measurable component of the universe, with specific properties that could be tested and constrained. The fate of the cosmos shifted from speculation to science. The data also humbled. Despite decades of effort, despite remarkable precision, dark energy itself remained mysterious. The measurements told us how much of it there was, how it affected expansion, how it evolved over time. But they did not tell us what it was. The nature of dark energy, its physical origin, its ultimate behavior, all remained unknown. The data constrained possibilities, but did not provide a definitive answer. It showed that the universe was accelerating, but not why, and so the data stands as both achievement and challenge. Achievement, because humanity has measured cosmic expansion across billions of years, mapped the universe's structure, and quantified its composition with unprecedented accuracy. Challenge, because the most important question, the nature of dark energy, remains unanswered. The data guides the next generation of observations, pointing toward what needs to be measured, what uncertainties need to be reduced, what tests need to be performed. It is not the end of the story, but a chapter, a foundation on which future discoveries will build. Beneath the data, beneath the measurements and observations, lies a deeper mystery. Dark energy is not just unknown, it is fundamentally strange. It does not behave like any form of matter or energy familiar from daily experience or laboratory physics. It does not clump into structures, does not decay over time, does not interact with particles except through its effect on the expansion of space. It seems to be a property of the vacuum itself, an intrinsic energy density that remains constant even as space grows. The more the universe expands, the more dark energy it contains, and the stronger its effect becomes. This behavior contradicts intuition. When you stretch ordinary matter, it thins out. A gas expanding into a larger volume becomes less dense. Energy disperses as space grows. But dark energy does not dilute. Each cubic meter of space contains the same amount of dark energy, regardless of how the universe expands. This means that as space grows, the total amount of dark energy increases, providing an ever stronger push that accelerates expansion. It is as if the vacuum itself has weight, negative pressure that pushes outward rather than pulling inward like gravity. Theoretical physics offers a possible explanation, the cosmological constant. In Einstein's general relativity, the equations describing spacetime allow for a constant term that acts like vacuum energy. Einstein introduced this term to keep the universe static, then abandoned it when expansion was discovered. But modern cosmology revived it as an explanation for dark energy. If the vacuum has an intrinsic energy density, if empty space itself exerts pressure, then the cosmological constant could drive acceleration. The mathematics works elegantly, fitting observations well, but there is a problem. When physicists try to calculate the vacuum energy from quantum field theory, the result is absurdly large, off by a factor of 10 to the power of 120 compared to the observed value. This discrepancy, sometimes called the worst prediction in physics, reveals a profound disconnect between quantum mechanics and cosmology. Either our understanding of vacuum energy is fundamentally wrong, or there is a mechanism that cancels almost all of it, leaving only the tiny residual we observe. Neither possibility is satisfying, and the mystery deepens. Alternative explanations propose that dark energy is not constant but dynamic, a field that changes over time. This field, sometimes called quintessence, could vary in strength, affecting expansion differently in different epochs. If quintessence exists, then the universe's fate might not be sealed. The acceleration we observe today could slow, halt, or even reverse in the distant future. Observations so far show no clear evidence of change, suggesting dark energy is roughly constant, but the possibility remains open. Understanding whether dark energy evolves requires even more precise measurements, extending further into cosmic history. Another approach questions whether dark energy exists at all. Perhaps instead, general relativity breaks down on cosmological scales. Maybe gravity does not behave as Einstein described when applied to the entire universe. Modified gravity theories attempt to explain acceleration without invoking dark energy, adjusting the equations to produce the observed effects. These theories face challenges. They must match not only expansion data but also other observations, the cosmic microwave background, galaxy distributions, gravitational lensing. So far, no modified gravity theory has succeeded as well as the simple cosmological constant. But research continues. The deeper mystery also touches on why dark energy dominates now. For most of the universe's history, matter and radiation dominated. Gravity shaped the cosmos, pulling matter into galaxies and clusters. Only relatively recently, about 5 billion years ago, did dark energy become the dominant component, driving acceleration. This timing seems suspicious, a cosmic coincidence. Why should we exist during the era when dark energy is just taking over? Some invoke the anthropic principle, suggesting that only in such an era could complex structures form and observers arise. Earlier, the universe was too dense and chaotic. Later, it will be too sparse and isolated. We exist now because this is when conditions permit it. This anthropic reasoning is controversial. It explains the timing but does so by invoking selection effects rather than physical mechanisms. It suggests that the universe's properties are not uniquely determined by fundamental laws, but selected from a range of possibilities by the requirement that observers exist to measure them. This line of thought leads toward multiverse ideas, where our universe is one among many, each with different properties, and we inhabit one where the conditions are right for life. Whether this constitutes science or philosophy remains debated. What makes the deeper mystery so compelling is its resistance to easy answers. Dark energy is not just another particle or field waiting to be discovered. It challenges our understanding of space, time, gravity, and quantum mechanics. It hints that something fundamental is missing from our theories, some principle or mechanism we have not yet grasped. Solving the mystery may require new physics, concepts that transcend current frameworks, breakthroughs that redefine how we think about the cosmos. For now, the mystery remains. Dark energy drives the universe toward accelerating expansion, shaping its ultimate fate. But we do not know what it is, why it has the value it does, or whether it will remain constant. These questions sit at the frontier of knowledge, inviting speculation, demanding observation, and resisting simple resolution. The deeper mystery is not a failure of science, but a sign of its vitality, proof that the universe still holds secrets, that the pursuit of understanding continues, that the story is far from over. The discovery that the universe's expansion was accelerating marked a paradigm shift as significant as any in the history of science. It overturned expectations, rewrote the future, and introduced a new actor into the cosmic drama. Before 1998, cosmology operated under a clear framework. The universe began with the Big Bang, expanded due to the energy of that initial event, and would eventually either collapse under its own gravity or expand forever, while gradually slowing down. Dark energy was not part of the picture. The future seemed straightforward, predictable from the amount of matter and the strength of gravity. After the supernova observations, that framework crumbled. Acceleration implied that some force was pushing space apart, overwhelming gravity's pull. This force, dark energy, was not a minor correction or subtle effect. It dominated the universe's energy budget, making up nearly 70% of everything. Matter, both ordinary and dark, was relegated to a supporting role. The future shifted from gradual deceleration to runaway acceleration, from a cosmos slowly winding down to one racing toward increasing isolation. The paradigm shift affected every aspect of cosmology. Models of structure formation had to account for dark energy's influence. Predictions about the ultimate fate of galaxies, stars, and black holes required revision. The timeline of cosmic history was recalibrated, marking the transition from matter domination to dark energy domination as a critical turning point. Textbooks were rewritten, courses redesigned, and research agendas redirected toward understanding this mysterious new component. Perhaps most profoundly, the paradigm shift changed how scientists thought about the universe's destiny. Before acceleration, the debate centered on whether expansion would continue forever or reverse into a big crunch. Both scenarios seemed plausible, each offering a different ending. After acceleration, the big crunch became unlikely unless dark energy changed dramatically. The heat death scenario, where the universe expands forever, cooling and darkening until nothing remains, emerged as the most probable fate. The cosmos was headed not toward collapse, but toward silence. This realization carried philosophical weight. A big crunch, for all its destructiveness, had symmetry, an ending that mirrored the beginning. It suggested cycles, the possibility of rebirth, a cosmic rhythm. Heat death offered no such comfort. It was a one-way journey toward increasing entropy, dispersal, and isolation. Galaxies would drift beyond each other's horizons. Stars would exhaust their fuel. Black holes would evaporate. Eventually, only a thin bath of particles and radiation would remain, spread so thinly that nothing could ever happen again. The universe would not end with a bang but with a whisper. The paradigm shift also highlighted humanity's ignorance. Dark energy was discovered not because someone predicted it from theory, but because observations demanded it. The acceleration was a surprise, a reminder that the universe does not conform to expectations. It showed that cosmology, despite its successes, remained incomplete. The most important component of the universe was unknown, its nature a mystery. This humility was healthy, driving scientists to question assumptions and remain open to unexpected discoveries. At the same time, the shift demonstrated science's strength. When data contradicted theory, the theory was revised. When observations revealed something new, the framework adapted. The process was not immediate or smooth. Skepticism, debate, and replication were all part of it. But ultimately, the evidence won. Acceleration became accepted, Because the data was compelling. Because multiple independent methods agreed. Because the result was robust. The paradigm shifted because reality demanded it. For the researchers involved, the shift was both exhilarating and unsettling. Exhilarating because they had discovered something fundamental, something that redefined cosmic fate. Unsettling because it raised more questions than it answered. What is dark energy? Why does it dominate now? Will it remain constant or change? These questions became the focus of intense research, driving the next generation of observations and theories. The paradigm shift was not an ending but a beginning, opening a new chapter in humanity's quest to understand the universe. The shift also resonated beyond science. Philosophers, theologians, and writers grappled with its implications. If the universe was destined for heat death, what did that mean for meaning itself? If everything would eventually fade into silence, did that diminish the significance of existence? Or did it make the present more precious, a rare moment of complexity and consciousness in a cosmos mostly empty and dark? These questions did not have scientific answers, but they arose naturally from the paradigm shift, connecting cosmology to deeper concerns about purpose and value. In retrospect, the paradigm shift fits into a larger pattern of cosmic humility. Copernicus showed that Earth was not the center. Hubble showed that the Milky Way was one galaxy among billions. Now, acceleration revealed that ordinary matter was not even the dominant component. We inhabit a universe made mostly of things we do not understand, dark matter and dark energy, living in a brief era when structure and light are possible. Our place in the cosmos is smaller, stranger, and more contingent than ever imagined. Yet the paradigm shift also affirmed human capability. Despite our smallness, despite our ignorance, we can observe, measure, and understand. We can detect acceleration across billions of light years and billions of years of time. We can map the universe's composition and predict its fate. We can ask profound questions and pursue answers with rigor and patience. The paradigm shift showed that the universe is knowable, even when it surprises us, even when it resists easy explanation. That is the true power of science, not certainty, but the capacity to learn, adapt, and grow in understanding. The discovery of accelerating expansion sent ripples through the scientific community and beyond. Immediate consequences that reshaped how we think about the cosmos and our place within it. The first ripple was realization, a dawning awareness that the universe we observe today will look radically different in the distant future. Galaxies that currently fill our telescopes will eventually drift beyond the cosmic horizon, their light unable to reach us across the ever-widening gulf of space. The observable universe will shrink, not in physical size, but in content, becoming emptier with each passing billion years. This means that future astronomers, if any exist trillions of years from now, will see a very different sky. They will inhabit a universe where only their local group of galaxies remains visible, bound together by gravity strongly enough to resist the expansion of space. Everything else will have receded beyond reach, carried away by acceleration until their light can no longer bridge the distance. Those future observers might conclude they live in a small, isolated universe containing only a handful of galaxies surrounded by infinite darkness. They would have no way to know about the billions of other galaxies that once populated their sky. This realization carries a haunting implication. We are privileged. We live during an era when the universe is still observable, when galaxies scatter across the sky in every direction, when the cosmic microwave background still glows faintly, carrying information about the Big Bang. We can study cosmic history because we exist during the window when evidence is accessible. Future civilizations, if they arise, will lack that opportunity. The universe will have hidden its own past, erasing the evidence of its origins and evolution. In that sense, we are the universe's witnesses during its most revealing age. The immediate ripple also affected predictions about galaxy evolution. Previously, astronomers thought galaxies would continue merging over cosmic time, gradually building larger and larger structures. But acceleration changes that picture. While gravity will pull together galaxies within clusters, It cannot overcome the expansion driving clusters apart. The cosmic web of filaments connecting galaxy clusters will dissolve. Clusters will become isolated islands, and within each island, galaxies will eventually merge into single massive elliptical galaxies. Our Milky Way and Andromeda are already on a collision course, destined to merge in about 4 billion years, forming a new galaxy in an increasingly empty cosmos. Another ripple touched the search for life beyond Earth. If the universe is accelerating toward increasing isolation, then civilizations that arise in the distant future will face profound loneliness. They will have access only to their local galaxy, unable to detect or communicate with life elsewhere. The window for cosmic communication, for interstellar or intergalactic contact, is finite. We live during the era when such contact is theoretically possible, when signals could traverse the distances between galaxies, when evidence of other civilizations might be detectable. This adds urgency to the search for extraterrestrial intelligence, a recognition that the opportunity is temporary. The immediate ripple also sparked philosophical reflection. If the universe is finite in observability, if future observers will have less information than we do, then knowledge itself is time-dependent. The cosmos reveals different truths at different epochs. This challenges the notion that understanding is always cumulative, that later generations always know more than earlier ones. In cosmology, at least, we may know more about the universe's large-scale structure than any future observers could. Our moment is not just rare but epistemologically privileged. Scientists also grappled with the implications for cosmic destiny. Acceleration meant that the heat-death scenario became overwhelmingly likely. The universe would not collapse, would not cycle, would not tear itself apart in a big rip, unless dark energy changed dramatically. Instead, it would expand forever, cooling and darkening, gradually exhausting its store of usable energy. This was not a sudden catastrophe, but a slow fade, a dimming of cosmic lights one by one until only silence remained. The immediate ripple was the recognition that this fate was not just possible but probable, written into the fabric of the universe by dark energy's relentless push. The ripple reached popular culture as well. Books, documentaries, and articles explored the discovery, bringing the story of accelerating expansion to wider audiences. People who had never thought about cosmology found themselves contemplating the universe's fate, wondering what it meant to live in a cosmos racing toward isolation. The discovery resonated because it touched on universal themes, endings, loneliness, the passage of time. It made abstract physics feel personal, connecting the fate of galaxies to the human experience of loss and change. For cosmologists themselves, the immediate ripple was both sobering and energizing. Sobering because it revealed how much they did not know, how the most important component of the universe remained mysterious. Energizing because it opened new avenues of research, new questions to pursue, new observations to make. The discovery of acceleration was not the end of inquiry, but the beginning of a new chapter, one focused on understanding dark energy and its implications for cosmic fate. The ripple also affected how scientists communicate uncertainty. Acceleration was accepted because the evidence was strong, but dark energy's nature remained unknown. This required explaining to the public that science can be confident about observations while remaining uncertain about explanations. We know the universe is accelerating. We do not know why. That distinction is crucial, a reminder that knowledge is layered, that some questions have firm answers while others remain open. The immediate ripple taught humility, both to scientists and to anyone following their work. In education, the discovery reshaped how cosmology was taught. Students now learn that the universe is dominated by components we do not understand, that the fate of the cosmos is bound up with the behavior of dark energy, that living during the observable era is a privilege. These lessons connect science to philosophy, encouraging students to think not just about data and equations, but about meaning, perspective, and the human place in an evolving universe. The immediate ripple continues today. Every new measurement of dark energy, every refinement of expansion rates, every observation pushing deeper into cosmic history adds to the picture. The ripple has not stopped because the discovery has not been fully absorbed. Its implications are still unfolding, still reshaping how we think about the universe and ourselves. And as the ripples spread, they carry with them a message that the cosmos is stranger and grander than we imagined, that our moment within it is rare, and that understanding is an ongoing journey rather than a final destination. To understand the universe's fate, we must recognize that we are not observing a static snapshot but echoes through time. Every observation of distant space is simultaneously an observation of the distant past. Light travels at a finite speed, and the farther away something is, the longer its light takes to reach us. When we look at a galaxy 1 billion light-years away, we see it as it was 1 billion years ago, when the universe was younger, denser, and behaving differently than it does today. This delay turns our telescopes into time machines, allowing us to study cosmic history directly. The cosmic microwave background is the oldest echo we can detect, light emitted when the universe was only 380,000 years old. At that moment, the cosmos cooled enough for atoms to form, allowing photons to travel freely for the first time. Those ancient photons have been journeying through space ever since, stretched by expansion into microwaves, arriving today as a faint glow filling the entire sky. This echo carries information about the early universe, its temperature, density, and composition, preserved like a fossil record from the dawn of time. The cosmic microwave background shows a universe that was remarkably smooth, with temperature variations of only a few parts per million. These tiny fluctuations were the seeds of all later structure, slight over densities that would grow under gravity's pull into the galaxies and clusters we see today. By studying the pattern of fluctuations, cosmologists can test models of cosmic evolution, measuring how fast the universe expanded, how much dark matter it contained, and when dark energy began to dominate. The echo from the earliest era constrains everything that came after. Closer in time, we can observe galaxies at different distances, seeing how they evolved over billions of years. High redshift galaxies, those very far away, appear as they were when the universe was young. They are often smaller, more irregular, more actively forming stars than nearby galaxies. They are building blocks, smaller systems that will merge over time to create the large spiral and elliptical galaxies common today. By comparing galaxies at different distances, astronomers can trace the assembly history, watching how cosmic structure grew from small seeds into the grand architecture visible in the present. Supernovae provide another kind of echo. When we observe a supernova in a distant galaxy, we are seeing an explosion that occurred billions of years ago. When the universe was expanding at a different rate, by measuring many supernovae at many distances, astronomers can map how the expansion rate changed over time. The data shows a clear transition, an epoch when expansion was decelerating, dominated by matter's gravitational pull, followed by an epoch when acceleration began as dark energy took over. This transition, occurring roughly 5 billion years ago, marks a turning point in cosmic history. The echoes through time reveal that the universe has aged. It was once hotter, denser, more chaotic. Star formation peaked billions of years ago, when gas was abundant and collisions frequent. Since then, the rate has declined. Many large galaxies have used up their gas or ejected it through supernova winds and black hole activity. New stars still form, but more slowly than before. The universe is middle-aged, no longer in the vigorous youth of early structure formation, but not yet in the quiet old age when star formation ceases entirely. These echoes also show how dark energy's influence has grown. In the early universe, matter and radiation dominated. Dark energy existed but contributed little to the total energy budget. As the universe expanded, matter and radiation diluted, spreading thinner across space. But dark energy remained constant per unit volume, meaning its total contribution grew as space grew. Eventually, about 5 billion years ago, dark energy surpassed matter in importance, and expansion began to accelerate. The echoes through time capture this transition, showing when the universe's fate was sealed. Looking forward, the echoes we observe today will change. Future astronomers, billions of years hence, will see fewer galaxies. Those that remain will appear as they were in a more recent past, closer in time to the observers. The cosmic microwave background will be even fainter, stretched by continued expansion, perhaps too dim to detect. The echoes will fade, not because the past is disappearing, but because the signals are being stretched beyond recognition or carried beyond the horizon, where they can never reach observers. The universe will hide its own history. This creates a poignant picture. We live during a privileged epoch when echoes from nearly the entire history of the universe are still accessible. We can see the cosmic microwave background from the earliest era. We can observe galaxies at high red shift from the epoch of formation. We can measure supernovae from the transition period when dark energy began to dominate. Future observers will lack this wealth of information. They will inhabit a darker, emptier cosmos with fewer clues about its origins and evolution. In that sense, we are witnesses to cosmic history at its most revealing moment. The echoes through time also teach humility. Every observation is a snapshot from a particular moment in cosmic history, and that moment is not representative of all time. The universe was different in the past and will be different in the future. What we see now, a cosmos filled with galaxies, lit by stars, structured by gravity and dark energy, is temporary. It is one chapter in a much longer story, a story that stretches from the Big Bang through the present and onward toward distant futures we can only imagine. For us, contemplating these echoes is an exercise in connection. The light reaching our eyes tonight began its journey long ago, carrying information across vast distances and vast times. When we study the cosmic microwave background, we are touching the early universe, feeling its warmth across billions of years. When we observe distant galaxies, we are seeing the cosmos as it was when Earth did not yet exist, when our sun had not yet formed, when the Milky Way was still assembling itself from smaller pieces. The echoes connect us to that deep past, making it tangible and real, and in those echoes we find our place. We are not outside cosmic history but part of it, observers living during one particular epoch, seeing the universe through the lens of our moment in time. The echoes remind us that everything is temporary, that even galaxies and stars are stages in a longer unfolding. They invite us to appreciate the present, this rare window when the universe is both structured and observable. When light from distant reaches still arrives, when the cosmic story is still legible, the echoes through time are gifts, messages from the past and future, whispering that we are part of something immeasurably vast and endlessly fascinating. Behind every measurement, every theory, every observation about the universe's fate, there are dreamers. These are the scientists who dedicated their lives to asking impossible questions, who looked at the night sky and wondered not just what was there, but how it would all end. Their names may not be as famous as explorers or inventors, but their contributions are woven into the fabric of human understanding. They are the cosmologists, astronomers, and physicists who refused to accept that the universe's destiny was unknowable, who built instruments, developed theories, and pursued answers with patience and passion. Vera Rubin was one such dreamer. She spent decades studying galaxy rotation, measuring how fast stars orbited around galactic centers. Her observations revealed that stars at the edges of galaxies moved just as quickly as those near the center, defying expectations based on visible matter alone. This discrepancy led to the discovery of dark matter, invisible mass that outweighs ordinary matter and shapes cosmic structure. Rubin's work showed that the universe was not what it appeared, that most of its mass was hidden, and that understanding cosmic fate required accounting for this unseen component. She persevered, despite skepticism, and her discoveries fundamentally changed cosmology. Saul Perlmutter, Adam Rees, and Brian Schmidt led the teams that discovered accelerating expansion. They spent years developing techniques to detect distant supernovae, coordinating observations across multiple telescopes, and analysing data with unprecedented care. When their results showed that expansion was speeding up, they initially doubted their own findings, checking for errors and systematic biases. But the data held. Their discovery earned them the Nobel Prize and revolutionised our understanding of cosmic fate, showing that dark energy dominated the universe and that the future held not collapse but endless expansion. Alan Guth proposed the theory of cosmic inflation, the idea that the universe underwent a brief period of exponential expansion in its earliest moments. This theory explained why the universe appears so uniform, why it has the geometry it does, and how tiny quantum fluctuations could be stretched into the seeds of galaxies. Inflation also raised the possibility that our universe is one among many, that the process of inflation might be eternal, continuously creating bubble universes with different properties. Guth's dream was to explain cosmic origins, and in doing so, he opened questions about cosmic endings and the possible existence of a multiverse. There are also the instrument builders, dreamers who translated scientific ambition into functioning technology, engineers who designed the Hubble Space Telescope, lifting it above Earth's atmosphere to capture images of unprecedented clarity, teams who built ground-based observatories in Chile, Hawaii, and the Canary Islands, sighting telescopes at high altitudes where the air is thin and steady. Satellite missions like WMAP and Planck required years of planning, fabrication, and testing, culminating in instruments that could measure the cosmic microwave background with exquisite precision. These dreamers made observation possible. Cosmologists are dreamers of another kind. They build simulations, using supercomputers to model the evolution of the universe from the Big Bang to the present and beyond. These simulations start with initial conditions based on the cosmic microwave background, then let gravity, dark matter, and dark energy interact over billions of years of simulated time. The results show how galaxies form, how clusters assemble, how the cosmic web develops. By comparing simulations to observations, cosmologists test theories and refine models. The dreamers who write the code and run the simulations are exploring the universe's fate through mathematics and computation. Theorists like Stephen Hawking dreamed of unifying physics, connecting quantum mechanics with general relativity, understanding black holes and the nature of time itself. Hawking's work on black hole radiation showed that even the darkest objects in the universe were not eternal, that they slowly evaporated over unimaginable time scales. This discovery had profound implications for cosmic fate, ensuring that even after stars died and galaxies faded, black holes would eventually disappear, leaving only a thin soup of particles. Hawking dreamed of a complete theory, and though he did not achieve it, his contributions shaped how we think about the universe's ultimate destiny. There are also the dreamers whose names we do not know, graduate students who spent nights at telescopes, postdocs who analysed data, technicians who calibrated instruments, teachers who inspired the next generation. Science is a collective endeavour, built on the work of many, and every contribution matters. The dreamers are not solitary geniuses, but communities, generations of people building on each other's insights, correcting each other's errors, and advancing understanding together. What unites these dreamers is a refusal to accept that the universe is beyond comprehension. They believe that observation, reason, and persistence can reveal truths about cosmic fate, even when those truths seem impossibly distant or abstract. They work with incomplete information, uncertain measurements, and provisional theories, yet they press forward. They face skepticism from peers, frustration when experiments fail, and the knowledge that definitive answers may not arrive in their lifetimes. But they continue because the questions matter, because understanding the universe's fate is part of understanding existence itself. For us, thinking about the dreamers is a reminder that science is human. It is not an impersonal accumulation of facts, but a deeply personal pursuit, driven by curiosity, wonder, and the desire to know. The dreamers give faces to abstract concepts, showing that behind every equation and every data set are people who cared enough to dedicate their lives to these questions. They remind us that understanding cosmic fate is an achievement of human imagination and effort, a testament to what we can accomplish when we reach beyond ourselves. The dreamers also inspire. Their stories show that anyone, regardless of background, can contribute to humanity's quest for knowledge. Vera Rubin faced barriers as a woman in science but persevered. Many cosmologists came from countries without large research budgets, yet they made critical discoveries. The tools of science, mathematics, observation, reason are available to all. The dreamers prove that the pursuit of understanding is open, that the questions are too large for any one person or nation, and that progress requires collaboration across borders and cultures. And so, as we contemplate the universe's fate, we honour the dreamers. They have given us the knowledge we now possess, the measurements, theories, and insights that allow us to peer billions of years into the past and billions more into the future. They have transformed abstract questions into concrete science, and they continue dreaming, planning the next telescopes, developing the next theories, pursuing the next observations. The story of cosmic fate is also the story of human curiosity, and the dreamers are its authors, writing chapters that will be read for generations to come. Science is often portrayed as a steady march towards certainty, but the reality is messier, more contentious, more human. Understanding the universe's fate has involved battles, not with weapons, but with data, theories, and interpretations. Scientists do not always agree. Different measurements give different results. Competing theories offer alternative explanations. The battle for truth is ongoing, a process of testing, debating, and refining that drives knowledge forward, even as it reveals how much remains uncertain. One of the most significant battles involves measuring the Hubble constant, the rate at which the universe is expanding. This number is crucial for determining cosmic age, size, and fate, but different methods for measuring it give different values. Observations of the local universe using Cepheid variables and supernovae suggest a Hubble constant around 73 kilometers per second per megaparsec. Observations of the cosmic microwave background, extrapolating from the early universe, suggest a value around 67. The discrepancy is small but persistent and significant enough that it cannot be explained by random error alone. This tension has sparked intense debate. Both methods are rigorous, both teams experienced, both results carefully checked, yet they do not agree. Some scientists suspect systematic errors in one method or the other, subtle biases that have not been identified. Others wonder whether the tension points toward new physics. Perhaps dark energy behaves differently than assumed, or perhaps the universe's expansion history is more complex than simple models suggest. The battle is not personal but scientific, a clash of evidence that demands resolution. Another battle involves the nature of dark energy itself. Is it truly a cosmological constant, an unchanging property of space, or is it dynamic, a field that varies over time? Observations so far show no clear evidence of variation, suggesting dark energy is constant within measurement uncertainties. But if it changes, even slowly, the universe's fate could differ dramatically from current predictions. Some theories propose that dark energy will eventually decay, allowing gravity to regain control and leading to a big crunch. Others suggest it will strengthen, leading toward a big rip. The battle is to measure dark energy precisely enough to distinguish these possibilities. There are also battles about alternatives to dark energy. Some physicists argue that rather than invoking an unknown energy component, we should modify our theory of gravity. Perhaps general relativity breaks down on cosmological scales, and a new theory is needed. Modified gravity theories attempt to explain acceleration without dark energy, adjusting Einstein's equations to reproduce the observed effects. But these theories face challenges. They must match not only expansion data, but also galaxy rotation curves, gravitational lensing, and the cosmic microwave background. So far, no alternative has succeeded as well as the simple cosmological constant, but the battle continues. The battle for truth also plays out in the search for direct detection of dark matter. Experiments deep underground look for collisions between dark matter particles and ordinary atoms. Particle accelerators search for signatures of dark matter production. Telescopes scan for gamma rays from dark matter annihilation. Despite decades of effort, no definitive detection has been made. Some scientists argue this means dark matter is more elusive than expected, requiring larger experiments and longer search times. Others wonder whether dark matter is fundamentally different from what theories predict, or whether modified gravity might explain some observations without requiring dark matter at all. These battles are not failures, they are the engine of progress. When different methods disagree, Scientists must investigate why, leading to improved techniques and better understanding. When theories compete, observations can test which one matches reality. When detection experiments fail, theorists refine predictions, and experimentalists design more sensitive instruments. The battle for truth is how science advances, through challenge, debate, replication, and refinement. The battles also reveal the provisional nature of knowledge. What we know about the universe's fate is based on the best available evidence, but that evidence is always subject to revision. New telescopes might reveal new information. New theories might reinterpret old data. The universe itself does not change, but our understanding evolves. The battle for truth reminds us that certainty is rare, that confidence must be proportional to evidence, and that science is comfortable with ambiguity, as long as it drives further inquiry. For the researchers involved, these battles can be frustrating. Spending years or decades on a problem, only to find that answers remain elusive tests patience and perseverance. But the battles also energize. The unresolved questions are what make cosmology exciting, what draw new minds into the field, what justify building ever more powerful instruments. If everything were known, the pursuit would end. The fact that battles continue means the universe still has secrets, and scientists still have work to do. The battle for truth also extends to communication. Scientists must explain not only what they know, but what they do not know, conveying both confidence in observations and uncertainty about interpretations. This is challenging because the public often craves definitive answers, clear statements about how the universe will end. But honest science requires acknowledging ambiguity, explaining that some questions have firm answers while others remain open. The battle is to maintain credibility while embracing uncertainty, to show that not knowing is not a weakness but a natural part of the scientific process. In the end, the battle for truth is not about winning or losing, but about getting closer to reality. Each measurement refines constraints. Each debate sharpens understanding. Each new method provides another angle of attack. The universe's fate may seem distant and abstract, but the process of determining it is immediate and human, filled with competition, collaboration, frustration, and discovery. The battle continues because the questions matter, because understanding cosmic destiny is one of the deepest pursuits humanity can undertake, and because truth, however elusive, is always worth fighting for. As the evidence accumulated, as theories refined and observations deepened, a new awareness emerged. It was not just that the universe had a fate, that it would end in some distant future. It was that we, living now, occupied a uniquely privileged moment in cosmic history. This awareness changed how scientists and philosophers thought about existence, about meaning, about the relationship between the fleeting and the eternal. It revealed that consciousness had arisen during a rare window, a brief era when the cosmos was both structured and observable. When stars shone and galaxies glittered, when the universe was young enough to remember its origins, yet old enough to have created the complexity necessary for life. The new awareness began with a simple realization. The universe has not always been as it is now, and it will not remain so forever. In the distant past, shortly after the Big Bang, the cosmos was too hot and dense for stars or galaxies to exist. It was a seething plasma of particles and radiation, opaque to light, chaotic and unstructured. Complex chemistry was impossible. Planets could not form, life could not arise. The early universe, for all its energy, was inhospitable to observers. In the blithe but distant future, if current understanding holds, the universe will be too sparse and cold. Stars will have exhausted their fuel. Galaxies will have drifted beyond each other's horizons, isolated by accelerating expansion. The cosmic microwave background will be too faint to detect. Space will be dark, empty, and silent. Any observers in that era, if they could exist at all, would see only their local galaxy surrounded by infinite darkness. They would lack the evidence needed to reconstruct cosmic history, unable to measure expansion or detect the Big Bang's afterglow. The universe will have hidden its own past. We live between these extremes. The universe is currently 13.8 billion years old, mature enough to have formed stars, galaxies, and planets. yet young enough that evidence of its origins remains accessible. We can observe the cosmic microwave background. We can measure galaxies at high redshifts. We can trace the evolution of structure from the early universe to the present. This combination of complexity and observability is temporary. A window, perhaps a few tens of billions of years wide in a cosmic timeline that may stretch infinitely forward. This new awareness carries profound implications. It means that the very act of doing cosmology, of asking about origins and fates, is time-dependent. The questions we can answer depend on when we ask them. Future observers will not have access to the same evidence. They might conclude that the universe is static, eternal, unchanging, not because they lack intelligence or curiosity, but because the data will be gone. The expansion that we measure will have carried distant galaxies beyond reach. The cosmic microwave background will have faded into noise. The universe will appear different not because it has changed fundamentally, but because observation is limited by what light can reach the observer. The new awareness also highlighted how contingent our existence is. We are not just rare in space, living on one planet among billions, but rare in time, existing during one epoch among countless others. The conditions that allow for complex life, for observers capable of studying the cosmos, are specific and temporary. Too early, and the universe lacks the heavy elements necessary for planets and biology. Too late, and the energy sources that power life will be exhausted. We inhabit the sweet spot, the era when the cosmos is fertile enough for complexity yet still visible enough to study. This realization brings both humility and wonder. Humility because it shows that our moment is not central or privileged by design, but simply lucky. We happen to exist during the window when cosmology is possible, when the universe reveals its secrets. Wonder because that luck is astonishing. The odds that conscious beings would arise during the epoch when understanding is possible seem vanishingly small. Yet here we are, asking questions that can still be answered, living in a cosmos that has not yet hidden its history. The new awareness also reframes what it means to search for extraterrestrial intelligence. If civilizations arise during the observable epoch, then we are not alone in time as well as space. Other observers, scattered across the universe, might also be studying cosmic fate, measuring expansion, detecting dark energy. But if civilizations arise too late, after the observable window closes, they will inherit a universe that appears small, isolated, and eternal. They might never know about the Big Bang, never discover expansion, never realize they live in a cosmos with a history and a fate. The search for intelligent life is not just a search across space, but across time, a recognition that observability is fleeting. For scientists, the new awareness added urgency. If the window is closing, if future observers will lack access to the evidence we currently possess, then documenting cosmic history becomes a responsibility. The measurements we make today, the theories we develop, the understanding we achieve, all of it is part of a legacy that may not be replicable. Future generations, whether human or other species billions of years hence, might look back at our era as the moment when the universe was understood, when observers had the good fortune to live during the time when evidence was abundant. The new awareness also touched philosophy and theology. If existence is time-dependent, if observers can only arise during specific epochs, does that suggest purpose or design? Or is it simply selection bias? The fact that we could only observe the universe during an era when observation is possible? These questions do not have scientific answers, but they arise naturally from the new awareness, connecting cosmology to deeper concerns about meaning, chance, and the nature of reality. In daily life, the new awareness might seem abstract, irrelevant to immediate concerns, but it shapes perspective. Knowing that we live during a rare window in cosmic time can make the present feel more precious. It reminds us that nothing lasts forever, not even the conditions that allow for understanding. It suggests that the act of observing, of asking questions, of seeking to know, is itself a gift, made possible by our fortunate placement in time. The new awareness does not answer the question of why we exist, but it clarifies when we exist, and what that timing means for our capacity to understand the universe and our place within it. After all the observations, all the theories, all the debates and refinements, a picture emerges. It is not complete, not free of uncertainties, but it is the deepest truth we currently possess about the universe's ultimate fate. If current understanding holds, if dark energy remains constant as observations suggest, then the cosmos is headed toward what scientists call heat death, a state of maximum entropy where all energy differences have dissipated, where no further change is possible, where the universe has reached its final equilibrium. This deepest truth unfolds over incomprehensible timescales. For the next several billion years, the universe will continue much as it is now. Stars will form, though at a declining rate as gas is used up. Galaxies will merge, including our own Milky Way colliding with Andromeda. Life will continue wherever conditions permit. The sun will eventually exhaust its hydrogen, swelling into a red giant and likely engulfing Earth before fading to a white dwarf. But these are local events, not cosmic endings. The universe as a whole will continue expanding, accelerating, carrying galaxies apart. Over trillions of years, star formation will cease entirely. The gas that fuels new stars will be used up, blown away by supernova winds, or locked into stellar remnants. The night sky, currently brilliant with young stars, will darken. The remaining stars will age and die, one by one. First the massive ones, burning brightly but briefly. Then sun-like stars, fading after billions of years. Finally the red dwarfs, the smallest and longest-lived stars, will exhaust their fuel after trillions of years. When the last red dwarf fades, the era of starlight will end. What remains are remnants, white dwarfs, neutron stars, and black holes. These objects do not shine but persist, held up by quantum effects or gravity alone. White dwarfs will cool over quadrillions of years, fading to black dwarfs, cold and invisible. Neutron stars will persist, dense and inert. Black holes will dominate, swallowing matter that drifts too close and merging when they encounter each other. For a time, black holes will be the last great structures, scattered across an expanding darkness, patient and enduring. But even black holes are not eternal. Through Hawking radiation, they slowly evaporate, losing mass particle by particle over timescales so vast they defy comprehension. A solar mass black hole takes 10 to the 67th power years to evaporate. Supermassive black holes, those millions or billions of times heavier, take far longer, perhaps 10 to the 100th power years. These numbers are so large that they lose meaning, but the principle is clear. Given enough time, all black holes will disappear, releasing their mass as faint radiation. When the last black hole evaporates, the universe enters its final phase. What remains is a thin bath of particles, electrons, positrons, photons, neutrinos, spread across ever-expanding space. Interactions between these particles become impossibly rare. Distances are so vast that particles effectively never encounter each other. Temperatures approach absolute zero. Energy differences vanish. The universe has reached maximum entropy, a state of perfect equilibrium where nothing can happen. This is heat death. Not a dramatic ending, but a slow fade into uniform stillness. The deepest truth is that this fate, while distant beyond imagining, is likely. Current observations suggest dark. Energy is constant, driving eternal acceleration. The universe will not collapse, will not tear itself apart, will not cycle. It will expand forever, cooling and darkening, asymptotically approaching a state where change becomes impossible. The heat death is not certain. Dark energy could surprise us, but it is the most probable outcome based on what we know. This truth carries philosophical weight. It suggests that the universe's story has a beginning and an end, not in the sense of a final moment, but in the sense of a transition from activity to stillness. The cosmos began with the Big Bang, a sudden expansion from a hot, dense state. It evolved through eras of structure formation, star birth, galaxy assembly, and accelerating expansion. It will end in silence, a vast emptiness where nothing happens, where the very concept of time becomes meaningless because there are no events to mark its passage. For some, this deepest truth is bleak, a universe that fades into lifelessness. That, exhausts itself and falls silent, seems to rob existence of ultimate meaning. If everything ends, if all structures dissolve, if even the memory of what once was disappears into entropy, then what is the point? This reaction is understandable, rooted in the human desire for permanence, for legacy, for something that lasts beyond our fleeting moment. But there is another way to see it. The deepest truth about cosmic fate does not diminish the present, it contextualizes it. We live during the vibrant era, the middle chapters, when the universe is alive with light, structure, and possibility. Our existence is rare, temporary, and precious precisely because it is fleeting. The fact that everything ends does not make it meaningless. It makes it significant. A song does not lose beauty because it ends. A life does not lack value because it is finite. And a universe, however vast, can hold meaning even if it is destined for silence. The deepest truth also invites gratitude. We exist during the epoch when stars shine, when galaxies glow, when the cosmic microwave background is still detectable, when the universe reveals its history. We can look outward and see billions of years into the past. We can trace structure from its earliest seeds to its present grandeur. We can ask about fate and receive answers grounded in observation. This capacity, this privilege, is fleeting. Future observers, if any exist, will lack it. We are the witnesses to cosmic history at its most observable moment. And so the deepest truth is not just about endings, but about perspective. It tells us that the universe is not eternal, that change is real, that everything we see is part of a grand unfolding toward an eventual stillness. But it also tells us that we are part of that story, that our moment within it matters, that the act of observing and understanding connects us to something immeasurably vast. The heat-death is distant, abstract, and perhaps inevitable. But here, now, in this brief, the window of time, the universe is brilliant, beautiful, and filled with wonder. That is the deepest truth we can hold. When you hold the knowledge of the universe's fate in your mind, when you understand that the cosmos is racing toward a distant silence, a question naturally arises. What does it mean? Not in a scientific sense, not in terms of equations or observations, but in a deeper, more personal way. What does it mean to exist in a universe destined for heat-death? To live during a temporary era of light and structure, to be conscious during the brief window when observation is possible? This question does not have a single answer, but pondering it connects cosmology to philosophy, science to the human experience of meaning and purpose. One way to think about meaning is through impermanence. Everything in the universe is temporary. Stars burn for billions of years, then fade. Galaxies shine for trillions, then darken. Even black holes evaporate. Nothing lasts forever. This impermanence can feel unsettling because we often associate value with permanence. We build monuments meant to endure, create art we hope will last, seek legacies that outlive us. The idea that even the universe itself is temporary challenges that association. But impermanence does not erase meaning. It creates it. A flower blooming for a day is no less beautiful than a mountain standing for eons. A life lived for decades is no less significant than a star burning for billions of years. Meaning arises not from duration but from presence, from the fact that something exists at all, from the connections it makes and the experiences it holds. The universe's impermanence makes this moment, this era of stars and galaxies and life, more precious, not less. Another way to ponder meaning is through rarity. We exist during a unique epoch in cosmic history. Too early, and the universe lacked the complexity necessary for life. Too late, and it will lack the energy and observability. We inhabit the sweet spot, the era when both structure and understanding are possible. This rarity is astonishing. The odds that consciousness would arise during the observable window seem vanishingly small, yet here we are, aware of the cosmos and our place within it. That awareness is itself meaningful, a cosmic lottery won against improbable odds. Connection offers another perspective. We are not separate from the universe, but part of it, made from its atoms, shaped by its laws, participants in its unfolding. The carbon in our bodies was forged in stars. The oxygen we breathe was released by stellar deaths. The iron in our blood was created in supernovae. We are stardust, quite literally, cosmic material organized into forms capable of thought and wonder. This connection means that the universe's fate is also our fate, not because we will be present at the heat death, but because we are expressions of the same processes that will eventually lead to it. Meaning also emerges from the act of understanding itself. Humans have looked at the night sky for thousands of years and asked questions. Where do we come from? Where are we going? What is our place in the grand scheme? For most of history, those questions were answered with myths, stories that gave shape to mystery. Now, through science, we can answer them with observations, measurements, predictions. The fact that we can understand the universe's fate, that we can trace its history and model its future, is itself a profound achievement. Meaning arises from that understanding, from the capacity to know. Some find meaning in the contrast between cosmic scales and human scales. The universe may be destined for silence trillions of years hence, but that has no bearing on our daily lives. We still love, create, build, connect. We still find joy in small moments, beauty in art, comfort in relationships. The cosmic perspective does not diminish these experiences. It frames them, reminding us that while our lives are brief, they are also real, valuable, and full of significance within their own context. Meaning exists at every scale, from the personal to the cosmic, and each is valid. Others turn to legacy. We cannot outlast the universe, but we can contribute to the collective human endeavour of understanding it. Every discovery, every observation, every theory refining our picture of cosmic fate is a gift to future generations. The knowledge we accumulate today will inform those who come after us, helping them see their place in time and space. Even if that knowledge is eventually lost when the universe grows dark and empty, it still mattered during the era when it was possible. Legacy is not about eternity, but about contribution within our moment. Philosophically, pondering meaning in a temporary universe raises questions about purpose. If the cosmos is not eternal, if it had a beginning and will have an end, does that imply intention or design? Or is it simply the natural consequence of physical laws? Science does not answer these questions. It describes how the universe behaves, not why it exists at all. The question of purpose remains open, a matter of personal belief, spiritual tradition, or philosophical stance. Cosmology provides context but not answers to the deepest why. For some, the lack of cosmic permanence is liberating. It means we are not bound by destiny, not constrained by eternal laws, but free to create meaning within our temporary existence. We decide what matters. We choose how to live. The universe does not impose meaning upon us, it offers us the opportunity to make it ourselves. That freedom is both daunting and empowering, a responsibility and a gift. Others find comfort in the vastness itself. Knowing that the universe is so large, so old, so filled with galaxies and stars, makes individual worries feel smaller. The problems that loom large in daily life, the stresses and anxieties, are placed in perspective by cosmic scale. This does not make them unimportant, but it offers a kind of peace, a recognition that we are part of something much larger, that our struggles are temporary, and that the cosmos continues its patient unfolding regardless of our concerns. Pondering meaning also connects to spirituality. Many religious traditions speak of the temporary nature of the physical world, the idea that material existence is fleeting, while something deeper, spiritual or transcendent, endures. Cosmology's story of heat death resonates with these themes, offering a scientific parallel to ancient teachings about impermanence and change. Whether one interprets this as affirming spiritual truth or simply as interesting convergence depends on personal belief. But the dialogue between science and spirituality enriches both, showing that questions of meaning are too large for any single perspective. In the end, pondering the meaning of the universe's fate is an invitation to reflection. It asks us to consider what we value, what we believe, how we understand our place in existence. The universe is vast, temporary, and indifferent to human concerns. Yet we are here, aware, capable of wonder, able to ask these questions. That capacity is itself meaningful, a rare and precious thing. The universe may end in silence, but here and now, in this fleeting moment, we are alive, conscious, and connected to the cosmos. That is meaning enough. We have travelled far, from the discovery of expansion to the nature of dark energy, from the early universe to the distant future, from measurements of cosmic fate to philosophical reflections on meaning. The journey has taken us across billions of light years and billions of years of time, revealing a universe more vast, strange, and temporary than our ancestors could have imagined. Now, gently, we return, not to a smaller world, but to a richer one, a world informed by cosmic perspective, connected to the grand story of existence. The legacy of understanding the universe's fate is profound. It represents humanity's capacity to transcend immediate concerns and ask ultimate questions. For thousands of years, people have wondered about endings, about whether time was linear or circular, whether the cosmos was eternal or created. Now, through careful observation and rigorous thought, we have answers, provisional but powerful. The universe began with the Big Bang, evolved through epochs of structure formation, and is moving toward a distant heat death. That knowledge is a legacy, passed from generation to generation, refined and expanded with each new discovery. This legacy changes how we see ourselves. We are not eternal, not central, not privileged by cosmic design. We are temporary expressions of matter and energy, arising during a brief window when the universe is complex enough to produce consciousness, yet young enough to be observable. Our moment is rare, and recognizing that rarity transforms perspective. It makes the present more precious, the act of living more significant, the opportunity to understand more valuable. The legacy is not just knowledge, but awareness, a deep sense of our place within the cosmic story. The legacy also lives in the tools and methods developed to study fate. The telescopes that measure distant supernovae, the satellites that map the cosmic microwave background, the simulations that model cosmic evolution, all of these represent human ingenuity applied to the largest questions. Future generations will inherit these tools, improve them, and use them to refine understanding further. The pursuit of knowledge is ongoing, each generation building on the work of the last, and the legacy ensures that the quest continues. But the legacy is also personal. Each of us, in contemplating the universe's fate, connects to something larger than ourselves. We join the long line of humans who have looked at the night sky and wondered. We participate in the collective endeavour of understanding existence. We contribute, even if only by listening, learning, and feeling awe. The legacy is not just for scientists, but for everyone who takes time to ponder the cosmos and their place within it. And so we return, not to ignorance, but to presence. The universe will continue its journey toward distant silence, but that journey unfolds over timescales so vast they are almost meaningless to human experience. What matters is here and now, this moment when stars shine, when galaxies glow, when life exists and consciousness asks questions. We live during the golden age of cosmic observation, when the universe reveals its secrets, and that age is also our home. Returning means recognizing that cosmic fate and human life are intertwined. The atoms in our bodies were forged in stars destined to die. The energy we use comes from a sun that will one day fade. The planet we inhabit orbits within a galaxy that will eventually merge with another. We are not separate from the universe's story, but woven into it, participants for a brief time in a process that began billions of years ago and will continue long after we are gone. The return also brings peace. Knowing the universe's fate does not burden us with dread, but offers perspective. The heat death is so distant, so far beyond human relevance, that it need not trouble our daily lives. What it does is frame our existence, reminding us that everything changes, that impermanence is fundamental, and that meaning arises not from lasting forever, but from being present now. The return is to the here and now, informed by cosmic knowledge but grounded in immediate experience. As you settle into rest, imagine the universe continuing its expansion. Imagine galaxies drifting apart, stars burning their fuel, black holes slowly evaporating. Imagine the distant future when space is dark and silent. Then bring your awareness back to now, to this moment, to the fact that you exist during the era of light. The stars still shine above you. The cosmic microwave background still glows faintly. The universe still reveals its history. You are part of that revelation, a witness to cosmic fate. The legacy of understanding is a gift, one that connects us across time to every human who has gazed at the night sky and wondered. It connects us to future generations who will continue the pursuit. It connects us to the universe itself, showing that we are not outside the story but within it, temporary expressions of cosmic processes, brief moments of awareness in an unfolding vastness. That connection is the deepest legacy, the knowledge that we belong, that we are part of something immeasurably large. And so the journey ends where it began, with wonder. The universe will end, eventually, in silence. But that ending is not tragic. It is natural, part of the rhythm of existence. Before the silence comes a long era of light, structure, and possibility. We are here during that era, fortunate beyond measure, able to observe, understand, and appreciate. The universe has given us consciousness, and we have used it to comprehend cosmic fate. That exchange, that gift, is the ultimate legacy. Rest now, knowing that the universe is vast but knowable, temporary but meaningful, silent in the distant future but brilliant in the present. You are part of its story, and that story, however it ends, is beautiful. The stars will continue their patient burning, the galaxies will continue their slow dispersal, and you, here in this moment, are connected to all of it. A thread in the cosmic tapestry, brief but essential. The legacy is yours to carry, and the return is to the peace of knowing you are home, here in the universe, now in this moment, part of the infinite unfolding. And so we arrive at the quiet end of our exploration through cosmic destiny. From the discovery of expansion to the mysteries of dark energy, from the heat death awaiting the distant future to the precious present we inhabit now, we have wandered through scales of time and space that stretch the imagination to its limits. The universe will continue its journey, expanding, cooling, eventually fading into silence. But that ending is so far beyond us that it need not trouble this moment. Thank you for joining me on this contemplation of ultimate fate, for letting curiosity guide you gently through the cosmos toward rest. If you found comfort in these reflections, I invite you to return whenever you need a quiet exploration beneath the stars. You can subscribe to ensure more journeys await you, more questions to ponder as you drift towards sleep. For now, let go of the distant future and rest in the present. Let the knowledge of cosmic fate settle gently, not as burden but as perspective. Breathe slowly, and know that you exist during the universe's most luminous age, when understanding is possible and stars still shine. Good night.